So far, we have seen that EMF can be induced by changing the magnetic flux. Now, in this topic, we are going to study the EMF by changing area of coil. So, let us see how we can induce the EMF by changing the area of a coil. So, for that, let us consider this diagram in which we have got this uniform magnetic field. So this is my uniform magnetic field which is going through this board, okay, which is threading this board like this. We have understood the notations also, and we have considered this rectangular coil PQRS. Now in the first case, what we see is, this is the first situation where this PQRS is outside the magnetic field, right? So that it has got the area, say A or S. Both are same. Okay, we have been using the notation for area as S. Okay, but in some book you may have area as A or S. Don't worry about this. Okay, you can use A as well as S. Now what we do is we apply the force to this rectangular coil. Force. Okay, so here we give force. What we are doing? We are giving force and we are pushing it in. Push towards this uniform magnetic field. Now whenever I push it towards the uniform magnetic field, there will be a velocity, and this velocity is uniform velocity. So there is one more thing, no acceleration. Okay, please check the spelling. There is no acceleration of this rectangular coil, and the length of this rectangular coil, one side is L, the other side is X, right? So first let us see, let it reach this point. Okay, first it reach here like this. Okay, it reach here. Whenever I push it, it reach here, and this is my, it is moving with the uniform velocity v, and it has traveled the distance of dx. Okay, and in time dt. In small time dt, it has traveled dx distance. Now in the second moment, let it reach here. Okay, let it reach here, and let this be the section. Okay, so let this be my dA or ds, right? This was the whole area. Whenever it is going inside the magnetic field, a small part is in the magnetic field. Similarly here also I will write dA, okay, and let this be again v, because the velocity is uniform, and this is my, say, dx, it has traveled dx in small time dt, and similarly this is v, it has traveled dx in small time dt. So this is the situation. So by changing the area, what we are doing is we want to find the EMF. So first, let this coil, this rectangular coil has reached this Q has reached Q dash, this R has come here, R dash, and this P has come here, P dash, and this S has reached here, S dash. That is my second condition. Right? Now we want to find the equation of EMF. So we know the equation of EMF, E is equal to minus N d phi by dt. Let this be equation number 1. So what is N? N is the number of turns, and number of turns is 1. How many turns of the coil is here? Only 1. So we don't write N, we just write 1. So what is minus? This minus is from Lenz's law, right? So this minus you may neglect, but I will not neglect. So this is the EMF. Now I want to find the equation for this dF, I mean flux, so that I can find the equation of EMF. So we know that the flux d phi is equal to B ds cos of theta. So what is theta? This theta is angle between, we know angle between B vector and ds vector, or इसको हम लिखेंगे dA vector. Okay, S or A both are same. So what is the angle? Can you say? The angle is 0 degree. Why? For that, so this is my rectangular coil, say PQRS. Okay, and this is my area vector. We know the area vector is always perpendicular to the plane of the paper, and it is like this, and this is the magnetic field which is going inside. So now I am moving this like this. So can you see what is the angle between magnetic field and this coil? Here what is the angle? It is 90 degree. But I want to find the angle between area vector and the magnetic field, not the angle between rectangular coil and the magnetic field. So if it is moving like this, then what is the angle now? Angle between this is area vector and this is magnetic field. The angle is 0 degree. If it was like this, then it should be 90 degree angle between magnetic field and the area vector, but it is just like this, that is 0 degree. So angle theta here is 0 degree. So this theta is equal to 0 degree. So therefore this is d phi is equal to b dA cos of 0 degree, and this 0 degree is 1. Okay, so dA, fine. You can write ds, no problem, or dA also. So this is the equation of flux. Now whenever you see here, whenever it is moving in the magnetic field, which is changing, whenever it is moving in the magnetic field, this L is, this PQ is not changing. This PQ, here also it is L, here also it is L, here also it is L, here also this is L. So this L is constant. Okay, so when PQRS is moving in magnetic field, L is constant, but X is changing. Can you see this? This was the total length, total breadth X. Whenever it is moved this much, this is small x dx. Again it is moved, small x dx. Again it is moved, small x dx. So dx is changing, but this this L is not changing. So then what we write? Therefore we write d phi is equal to B. D is there, and what is S? S is my area. You know that S is equal to area, and area of rectangle is length into breadth, right? And this is length L into what is breadth? Breadth is X. Okay, length is L, breadth is X. So here I will write S is area. Here I will write ds. Instead of ds, we write L into X, and which is equal to B. L is not changing. I will take outside, and there will be dx. So d phi is equal to BL dx. Understood? Why I am writing this dx here? Because this dx is changing, but L is not changing. If it is moved dx, L is same, L is same. So we got each and everything. So let me put it off. Now what do I get? Substitute the value of d phi in equation 1. We get this E is equal to minus, in denominator I have got dt, d phi. What is the value of d phi? Is B, L and dx, right? So this will be equal to minus BL dx by dt. So now what is dx by dt? Dx by dt is V. Okay, we know rate of change of velocity, rate. Okay, so velocity is equal to rate of change of position, dx by dt. So this dx by dt will be equal to minus BLV. So this is the EMF induced by changing the area of this rectangular coil. Now in some time we can also write this E is equal to BLV, no problem. Well, I have not written the negative sign because this negative sign has come from only the Lenz's law. Now one more thing is there, that we find the EMF. Okay, equation of EMF. Now what should be the direction of current in this loop? P dash, Q dash, R dash and S dash. What should be the direction? So to find the direction of the current, we use the Lenz's law. Okay, and we have also studied to find the direction of induced current, we can also use the Fleming's right hand rule. Please remember, there are two laws of Fleming's. One is Fleming's left hand rule and one is Fleming's right hand rule. So Fleming's left hand rule is used to determine the force on conductor, whereas the Fleming's right hand rule is used to determine the current. Rest is same. So if we use this as Fleming's left hand rule, father, mother, child. Father is force, mother is magnetic field, child C is current. So we want to find the direction of current. So to use this, how do we use? It is same as the Fleming's left hand rule, father, mother, child, force, magnetic field and current. So this coil is moving in this direction. So this is the velocity in this direction and this is the force in the same direction. So father is force, so I have to point this force towards this. This is the father, right? And if you see here, magnetic field. What is the direction of magnetic field? This is cross, so this magnetic field is going inside. Then this should be the direction of current. It should be in this direction, upward direction, upward direction. So direction of the current here should be what? R to Q, Q to P, Q to S. Because whenever it move here, this R, S will move here, and this is the force, this is the magnetic field going inside, and this is the current. So first the current will start moving from R to Q. So the direction of current is determined by using Fleming's right hand rule or Lenz law, and the direction of current is from R to Q, Q to P, P to S. Okay, so this is the direction of current. Or you can also write here, it is from R dash to Q dash, P dash to S dash. R dash to Q, Q dash to P dash, P dash to S dash, both are same. And the EMF induced by this process is called motional EMF, because the EMF is produced by moving the coil into the magnetic field. So the EMF is also called motional EMF. Thank you.